Chapter 9 deals with chemical equilibrium, and one thing that you can always do is you can focus on the equilibrium equation and write the Kc expression. In this equilibrium equation, Kc is equal to, it's always products over reactants raised to their appropriate coefficients. This question is asking, what is Kc going to be? So it's going to be the concentration. The subscript C stands for concentration. So in the numerator, we'll put a square bracket NH3 squared divided by, and in the denominator we'll put nitrogen in square brackets times hydrogen cubed. Okay, first of all, remember that the square brackets stand for concentration in units of moles per liter. And to write the form of the Kc equation, we will always take the products over reactants and raise them to their appropriate coefficients. So ammonia squared is the product divided by the concentration of nitrogen and the concentration of hydrogen cubed. Now in this problem we do not use the ICE table because this is already at equilibrium. So we're told that this is an equilibrium mixture. This is already at equilibrium, therefore we do not use the ICE equation. This is already at equilibrium, and therefore we do not use an ICE table. Instead, we plug in the concentrations. Now, when we plug into the concentrations, keep in mind that concentration is in units of moles per liter. We divide the number of moles by the volume. So we're given the number of moles of each substance, 1.5 moles of nitrogen, for example, but it's in a 2-liter vessel. It's going to be 1.5 divided by 2. This is the number of moles of hydrogen in a 2-liter vessel. This is the number of moles of ammonia in a 2-liter vessel. And so we can write over here that the concentration of ammonia, which is going to go into the numerator, is going to be 4 divided by 2 liters. This is moles over liters. So we have to express this in concentration. If you don't express it in concentration, you'll get it wrong. This is equal to 2 moles per liter. And for the nitrogen, N2, the concentration of nitrogen at equilibrium, we have 1.5 moles divided by 2 liters. And that calculates out to be 0.75 moles per liter. And the concentration of hydrogen that's given at equilibrium is equal to 2.7 moles divided by a 2-liter container. Always express this in concentration, not in moles. If you express it in concentration, you'll get it wrong. And when we divide 2.7 by 2, we get 1.35 molar. So with that in mind, we can plug those numbers into this equation to get the answer. So that Kc is equal to, at equilibrium, the concentration of ammonia is 2.0. And we square that. It's products over reactants squared. So the concentration of ammonia is 2.0 moles per liter. We square it. Divided by the concentration of nitrogen, which is 0.75. And divided in the denominator by the concentration of hydrogen, which is 1.35. And that has to be cubed. So when we calculate this out, we get 2.2 as the answer. This is the equilibrium constant Kc for this reaction. Remember that K does not have any units. So even though we had moles per liters here, K by definition is a dimensionless term. It does not have any units, and that's the value of Kc. Okay, look at the next problem. This says for this reaction, we have an equilibrium constant Kp that is this temperature. Is this value at this temperature, and at equilibrium we're given the partial pressure of hydrogen. What is the equilibrium partial pressure of ammonia? Now once again, no ICE table is needed. No ICE table is needed because this is already at equilibrium. We do not need an ICE table because this describes what's at equilibrium. ICE tells us we're not at equilibrium. This already says here's the Kp value. This is an equilibrium value. So what's the equilibrium partial pressure of CH4? Okay, well, as I look at this equation, the important thing to remember is that in a heterogeneous reaction, this is very important, in a heterogeneous reaction, we always omit any solid or liquid from the Kc or Kp equation. Omit any solid or liquid from, we can just say, the Keq equation. Okay, so notice that this is a solid, and since it's a solid, we're going to omit it. So let's write the form of the equilibrium constant equation. We're given the value of Kp. Kp is equal to the partial pressure of the product, CH4, divided by the partial pressure of the reactant, hydrogen, H2, and that is squared. We raise it to a power equal to what its coefficient is, and we leave carbon out. Carbon is a solid. This is a heterogeneous reaction. You only include the gases. Now, in this case, I know what Kp is. Kp is equal to 0.262 at this temperature. And we're given the partial pressure of hydrogen. So I can have here the partial pressure of CH4 divided by the partial pressure of hydrogen is 1.22 squared, and that's equal to 0.262. Now, in order to do a Kp, the partial pressure must be expressed in atmospheres. So Kp is in terms of the partial pressure of each substance in atmospheres, partial pressure of each gas in atmospheres. Okay, so I have one equation, one unknown. I know Kp, I know the partial pressure of hydrogen, and I can solve for the partial pressure of methane. Therefore, the partial pressure of methane, when I calculate this out, I get 0.390 atmospheres. It will be in atmospheres. Okay, the next question says, here is an equilibrium, and we have an equilibrium mixture. Now, once again, if you already have an equilibrium mixture, you do not use an ICE table. This is an equilibrium mixture. We're given the number of moles and the volume of the container. So what we want to do here, this asks, what is Kc? Well, Kc is equal to the concentration of C squared divided by the concentration of A and divided by the concentration of B squared. That's the value of Kc. It's products over reactants. So square brackets stand for concentration, and the concentration is expressed in units of moles per liter. So what is the concentration of C in units of moles per liter? Well, for Kc here, the concentration of C in units of moles per liter is 3 divided by 1, or 3 moles per liter, and that's going to be squared in the numerator. I have to square it because the coefficient is 2. Divided by the concentration of A, well, we have 4 moles of A in a 1 liter container, so that's 4. And the concentration of B is 1 mole in a 1 liter container, so that's 1 squared. And so when we multiply that out, we're going to have 3 squared divided by 4 calculates out to be 2.25. Again, I do not need an ICE equation because it's already at equilibrium. It's already at equilibrium. The next question says, if we have this equilibrium that exists, and we're given the Kc this time, in this case we're given the value of Kc, and we're told how many moles of each substance are present in this 1 liter container, then is the system at equilibrium? Is the forward reaction occurring? Is the reverse reaction occurring? What will we have? Well, in this case, we have to calculate the reaction quotient. QC has the same form as Kc in that it's products over reactants. It's just that it may or may not be at equilibrium. QC is going to be the concentration of C squared divided by the concentration of A and the concentration of B. It's just products over reactants. This is just the quotient we get when we plug in the concentrations at any particular time. So when I plug this in, I have 10 moles of C in a 1 liter container, so the concentration of C is 10, and I've got to square this. The concentration of A is 2, and the concentration of B is 4. And so when we calculate QC, we get 12.5. Now that's the value of QC, and we have to compare it to KC. So KC is 25, QC is 12.5, therefore QC is less than KC. Now since both K and Q have the products over the reactants raise their coefficients, if if Q is not equal to K, it's not at equilibrium, but all of nature is headed toward equilibrium. This reaction is going to head toward equilibrium, and the way that it will do this number is too small. 12.5 is too small. It needs to be 25. How can I make this 12.5 a bigger number? By having a larger numerator and a smaller denominator. The numerator is the reactants. I need more reactants and less products. And so this is going to go in a forward direction. And the correct answer to this question is choice A. The forward reaction predominates. The forward reaction occurs. Now, one way to remember this and to keep this straight is to think of the number line. On the number line, K is some positive number on the number line. And if Q is less than K on the number line, the reaction is going to head in a forward direction until you reach equilibrium. If Q is bigger than K on the number line, the reaction will go in a reverse direction until you reach equilibrium. The next question is going to be similar to this. We're going to be given some initial concentrations, and we're given the value of K, and we're asked what's true about this reaction. So it's we don't know if this is at equilibrium or not. So we plug these values into the reaction quotient equation, which looks just like the Kc equation. The reaction quotient is equal to the concentration of C divided by the concentration of A and divided by the concentration of B squared. So it's always products over reactants raised to their appropriate coefficients. Now, when we plug this in, this is already in terms of concentration, so we just plug these numbers in. C is 0.80 divided by the concentration of A, 0.10, and divided by the concentration of B, which is 0.20. Now be sure to square this because of the coefficient on B. So when you plug this in and calculate this out, we get 200. 200 is what we get. And therefore, QC is less than KC. In order for the reaction to reach equilibrium, I need a bigger numerator and a smaller denominator so that this will end up being equal to K. And so, once again, since Q is less than K, the forward reaction occurs. So on this question, the correct answer again is that the forward reaction occurs. The next question says, suppose that we have these concentrations initially. If these are our initial concentrations, let's calculate Q again. QC is equal to the concentration of C over the concentration of A times the concentration of B squared. This looks just like K, it's just that these concentrations may or may not be at equilibrium. So let's plug these numbers in. QC is equal to, each of these is 1. 1 divided by 1 times 1 squared, which obviously is 1. And K is 300. Once again, Q is less than K, and the forward reaction occurs. Okay, this seems like a simple question, so why did I include this as an example? I included this because a lot of students, for some reason, they assume that K must be 1. K is not 1. K is 300 in this case. K is hardly ever 1. I'm not aware of any reactions under normal conditions where K is equal to 1. In this case, Q is equal to 1. We have all these concentrations, but that's not K. K is 300. And 1 is less than 300. The reaction has to go in a forward direction. We look at the next question, and in this case, we've got 0 of A and 0 of B. So when I calculate Q here, QC is equal to the concentration of C, its products over reactants, divided by the concentration of A and the concentration of B squared. So let's plug the values in. C is 1 in the numerator, A is 0, and B is 0, so 0 squared. Now that number is undefined. You cannot divide by 0. This is an undefined number. However, you know from calculus that the limit as x approaches 0 of 1 over, this would be x cubed, as x approaches 0, the limit of 1 over x cubed is equal to infinity. As the denominator gets smaller and smaller, this number becomes infinitely large. So I'm not saying that 1 divided by 0 is infinity, but you can think of the limit as this gets increasingly small is infinity. And as we look at this, at equilibrium, you will always have some of everything. So which is bigger? Is infinity bigger or is 300 bigger? Well, infinity is bigger than 300. Therefore, Q is larger than K. And on the number line, if this is K and if Q is larger than K, then the reverse reaction is going to occur. Now, don't let the fact that this is undefined. If you have 0 in the denominator, it's going to go in the other direction. Let's look at it this way. Let's write the equilibrium. A plus 2B in equilibrium with C. And let's write our initial concentrations. The initial concentration of A is 0. The initial concentration of B is 0. The initial concentration of C is 1. Anytime you're at equilibrium, every equilibrium system contains some of each reactant and product. You will never have 0 of something if there's an equilibrium. You'll never have 0. So how can I get some of every reactant and product? It's by C reacting and coming in this direction. On the change line, it's going to be C. It's going to be minus X. We're going to lose C. We're going to gain A. For every X moles of C that reacts, we will get X moles of A and we'll get 2X moles of B, until finally at equilibrium in our ICE table we will have X moles of A, 2X moles of B, and 1 minus X moles per liter of C. So we will always have some of every reactant and product at equilibrium. And so if you have 0 reactants, then it's got to go in a reverse direction. Let's look at the next question. The next question is similar to this. So if I write Q for this equation, QC is equal to, it's going to be product, C is 1, divided by the reactants, A is 1, and B is 0. That's going to be 0 squared because this is raised to the power of 2. Well, once again, this is an undefined number. You cannot divide by 0. However, once again, I would say that the limit of 1 over x as x approaches 0 is equal to infinity. You can think of this as being infinitely big. And which is bigger, infinity or 300? Well, infinity is bigger than 300. Q is greater than K, so the reverse reaction is going to occur again. Now, in this case, let's look at it one more time in terms of the ICE table. In terms of the ICE table, if I put A plus 2B in equilibrium with C, if my initial concentration of A is 1, the initial concentration of B is 0, the initial concentration of C is 1, this cannot be at equilibrium because it's not at equilibrium initially because I have 0 of B. Anytime you have equilibrium, you'll have some, it may be a very, very tiny amount, but you'll have some of each reactant and product. And so this has to go back in the reverse direction in order to give us some of this. It's going to go in a reverse direction, so this will be minus x over here, plus x, and plus 2x on the change line. So the equilibrium line will be 1 plus x, this would be 2x, and this would be 1 minus x. At equilibrium, we will get that those amounts, and these will be numbers greater than 0. Okay. In the next question, what if you have this as the initial concentration? So let's write Q again. Now remember that QC is equal to products over reactants. It's the concentration of C divided by the concentration of A and the concentration of B squared. And if I plug these values in, C is 0, divided by A is 1, and B is 0 squared. Okay. Now this again is undefined. But taking the limit does not help us in this case. Instead, let's look at the ICE table. A plus 2B in equilibrium with C, where initially I have 1 mole per liter of A, 0 of B, and 0 of C. If this is initial, what would go on the change line? Well, it can't go forward because if I go minus x minus 2x plus x, if it went forward, we would be reacting some of this. But you can't react any B because there's not any to react. You can't spend more money than you have. If B is already 0, you can't react it. It can't go forward. So it can't go forward. It can't go forward. So let's just scratch that out. So let's look, what if it goes in reverse? So to go in reverse, if the change line was plus x over here, plus x, plus 2x, minus x. Well, again, it can't go in reverse because there's not any c. It can't go in reverse. It's not at equilibrium. This is not equal to 300. K is equal to 300, and this is not equal to 300. So the correct answer to this is none of these. You can never reach equilibrium. If all you have is A, and A needs some B to react with it, it can never establish this equilibrium. You've got to have some B in there to react with A in order for this equilibrium to exist. Okay, now let's look at the next one. This says we're given 0.7 moles of NO2. It's in a 1 liter container. And the question asks, when the reaction shown below has reached equilibrium, the concentration of NO2 is found to be this much. And so what is the value of the equilibrium constant? Now, for some reason, this kind of question is one that students often have a lot of difficulty with. We're given the initial amount of one of the substances, and we're given one equilibrium amount and asked to find K. This is a very straightforward question, but let's take a look at it and see what you need to do so that you can get this correct. So I'm going to set up the ICE table. I'll set up initial, change, equilibrium. The initial concentration of NO2, I have 0.7 moles in a 1 liter container. This is 0.70 moles per liter. So that's the initial concentration. Now, what is the initial concentration of nitrogen monoxide? The initial concentration of nitrogen monoxide, this just says we put nitrogen dioxide in a container. It doesn't say anything about nitrogen monoxide or oxygen. So we use exclusive language in chemistry. If we say we put nitrogen dioxide in a container, that means we did not put any nitrogen monoxide or any oxygen in the container. There's zero of this. We use exclusive language. If I say I put this in a container, that means I exclude anything else. I did not put anything else in. Well, as I look at this, I can tell that Q is equal to 0. Q is equal to, in the numerator, 0 squared times 0, 0 squared times 0, divided by 0.7 squared, which is 0. I don't even know what K is. That's what we're being asked to determine. But K is always a positive number. It may be a very small positive number, but it's a positive number. Therefore, Q is less than K. It has to go in a forward direction. To go in a forward direction on the change line, I will put minus 2x. For every 2 moles per liter of this that react, I will get 2x moles per liter of NO, and I will get x moles per liter of oxygen. So it's going forward, so I put a negative sign on the reactant side because we're losing reactants. That's what it means when we say we're going forward. I put a positive sign on the product side because if it's going forward, we are gaining products, and I have to bring the coefficients down. So it's minus 2x plus 2x plus x, and this will be 0.7 minus 2x, 2x, and x. At equilibrium. Those are the equilibrium values right here. Well, once we have this and once we read the information, this says that when the reaction reached equilibrium, the concentration of NO2 was found to be 0.28 moles per liter. Now, notice what they're telling us. This 0.28 is the concentration of NO2 at equilibrium, and the concentration of NO2 at equilibrium is on this line. This 0.28 is the same as 0.7 minus 2. That's the concentration at equilibrium. So let's just jot this down. The concentration of NO2 at equilibrium, from the EQ line, we know it has to be 0.7 minus 2x, but we're given that the concentration at equilibrium is 0.28. So this is one equation with one unknown. We can solve for x. To solve for x, let's just get the 0.7 term on the other side. I'll have negative 2x equals negative 0.42. I've subtracted 0.7 from both sides. I divide both sides by negative 2, and x is equal to 0.21. That's the value of x here. Now, if that's the value of x, then I know each of these terms. And so, therefore, I can calculate Kc. Now, be sure you understand how to do this. A lot of students have difficulty with this kind of problem. We were given the initial concentrations, and we were given one of the equilibrium concentrations. That allows us to figure out what x is, so I know what x is. And so, notice then, the concentration of NO at equilibrium is equal to 2x. I get that from the EQ line, 2x, which is 2 times 0.21, which is 0.42. And the concentration of O2 at equilibrium is equal to x, which is 0.21. So now to calculate Kc, Kc is equal to the concentration of NO squared times the concentration of oxygen divided by the concentration of NO2 squared. It's products over reactants raised to their appropriate coefficients. And remember that the only time it's equal to the equilibrium constant is at equilibrium, but that's what the EQ line on the ICE table tells us. This is the equilibrium concentration. So the concentration of NO at equilibrium we saw is 0.42. 0.42 squared. The concentration of oxygen at equilibrium is 0.21. Let's just put parentheses here. That's in the numerator. The concentration of NO2 at equilibrium was given to us. It's 0.28. And we have to square it because the coefficient of 2 is here. And so when you calculate that out, Kc is equal to 0.47. Remember that equilibrium constants do not have units. So this is a dimensionless term. There's no units. Kc is equal to 0.47. For the next question that we look at, what we need to do is, we're going to need more space for this. So let's set this up on a different sheet of paper and work through it. Okay, so for number 12. Okay, number 12 says at 250 degrees C, this reaction has this equilibrium constant. If we put 0.2 moles of PCl5 in a 5-liter container, what will be the equilibrium concentration of chlorine? So when we set this up, when all else fails, you do two things. You set up the ICE table. If you're stuck and don't know anything else to do, set the ICE table, and then plug the EQ values, the equilibrium values, from the table into the KEQ equation. From the table into the KEQ equation. Okay, so here's what we're going to do in that case. I'm going to rewrite the balanced equation. PCl5, a gas, in equilibrium with PCl3, a gas, plus Cl2, a gas. You need the balanced equation here. Then we will put the initial amount, the change, the equilibrium amount. Now remember, this has to be expressed in terms of concentration. So we had 2 moles of PCl5 in a 5-liter container. So I need to plug in concentration. So over here I'm going to put that the concentration of PCl5, the initial concentration, I'll put a subscript 0, that means at time t equals 0, this is initial, is equal to 0.2 moles divided by 5 liters, because, concentration is moles per liter, and that calculates out to be 0.04. 0.0400 molar. That's the initial concentration. So I plug that in here. The initial concentration is 0.0400. Now be sure that in the ICE table, if we're given Kc, and we were given Kc, Kc is 1.8, you have to plug in concentration. The subscript C stands for concentration. You have to put in concentration and not number of moles. If you put in number of moles, you'll get it incorrect. So if 2 moles of PCl5 is placed in a 5-liter container, then what will be the equilibrium concentration of chlorine? Now, all it says is we put this in here. So what is the initial concentration of PCl3? It's 0 because we use exclusive language. If we say we put PCl5 in the container, that means we didn't put anything else. We didn't put any PCl3 or any chlorine. Now, in this case then, as I look at this, Q is equal to 0 times 0 divided by 0.04, which is 0. 0 is less than 1.8. This has to go in a forward direction. What does it mean that it goes in a forward direction? It means that we're going to lose reactants, so minus X moles per liter of PCl5. Now draw a line here, because when you add up 0.04 minus X equals, that line you pronounce equals. So minus X over here, but for every X moles per liter of PCl5 that reacts, we will get X moles per liter of PCl3, and we will get X moles per liter of chlorine. Now we add these up vertically, and we'll have 0.04 minus X. Now there's three significant figures. I'll use those three significant figures at the end. 0 plus X is X, 0 plus X is X. And so that's what we see on the equilibrium line. So when all else fails, set up the ICE table. This is the ICE table. And then plug the equilibrium values, that's these numbers, plug them into the KEQ equation. So let me write the KEQ equation. It's Kc. We were given the value of Kc. Kc is the concentration of PCl3 times the concentration of chlorine divided by the concentration of PCl5. That's the definition of the equilibrium constant. It's always products over reactants raised to their appropriate coefficients. The coefficients are all 1, so they're all raised to the power of 1. Kc is given. I'm going to go ahead and write over here what Kc is. It's 1.80. So we were given Kc. K does not have any units. So that's the Kc equation. Let's plug in these values from the equilibrium line. Concentration of PCl3 is X in the numerator, and the concentration of chlorine is X. So in the numerator, I'll have X squared. X times X is X squared, divided by the concentration of PCl5, 0.04 minus X. That equals 1.80. Okay. Now we've got to solve for X. So what I need to do next here is I look at this is I want to cross multiply to get this value out of the denominator. So I'll have X squared equals 1.80 times 0.04 minus X. Next I will multiply across to remove the parentheses. X squared equals, in 1.8 times 0.04 is 0.072 minus 1.8 X. It really has three significant figures. I'll fix the significant figures at the end. Now we'll get all this is a second order polynomial. We'll have to get all the terms on the other side. So I'll have X squared plus 1.8X minus 0.072 equals 0. That's just algebra. I add 1.8X to both sides. I subtract 0.072 from both sides. This is in the form of a second order polynomial, in the form of AX squared plus BX plus C equals 0. Be prepared for a quadratic formula question. You may have to use a quadratic formula in order to solve one of these questions on the exam. The quadratic formula is that X is equal to negative B plus or minus the square root of B squared minus 4AC, all divided by 2A. So I'll plug these coefficients into this, and X is equal to, and negative B is 1.8, so this is negative 1.8 plus or minus the square root of 1.8 squared, because that's what B is, 1.8, minus 4 times A. Well, what is A? A is 1, times C. What is C? C is negative 0.072. Okay, and that's divided by 2A, and A is 1. Now, I think what I'm going to do in this case, let me just do this out to the side. I'll have negative 1.8 plus or minus. Now, if I do everything underneath the radical, and if I take the square root, I'll get plus or minus 1.878297 divided by 2. That's what I get whenever I plug that in. So let's continue with X then. In a second order polynomial, when you solve for X, you always get two roots of X. Okay. Now, as I go back to the ICE equation, see, negative 1.8 plus 1.87 is going to be a positive number, because 1.87 is bigger than negative 1.8. The magnitude is greater, so that would be a positive number. Or negative 1.8 minus 1.87. Well, if I go back to the ICE table here, x must be between 0 and 0.04. X has to be a positive number. It's going in a forward direction. If x is negative, that would make no sense. If I said 0 minus an amount, that would give me a negative concentration. You can't have a negative concentration. X has to be positive, and x has to be less than 0.04. So, therefore, x is greater than 0 and less than 0.04. And so when I look at that, it cannot be negative 1.8 minus 1.87. I can rule out the negative result. X must be the positive result. Negative 1.8 plus 1.878297 is, in the numerator, 0.078297 divided by 2, which is 0.0391. 0.0391. So we found x. Now, here's a suggestion that you have to especially watch when you are doing equilibrium problems, and that is always answer the question that was asked. Always answer the question that was asked. Okay, you don't want to do all this work and then choose the wrong answer because you were not answering the question that was asked. So look at the question that was asked. This says, if 0.2 moles is placed in a 5-liter container, what will be the equilibrium concentration of chlorine? What will be the equilibrium concentration of chlorine? The equilibrium concentration of chlorine is right here on the ICE table. It is X, and that's what we solved for. So the equilibrium concentration of chlorine is X. The concentration of chlorine at equilibrium is equal to X equals 0.0391 moles per liter. And so that is the answer to this question, 0.0391 moles per liter. Always answer the question that was asked. Concentration of chlorine at equilibrium equals 0.0391 moles per liter. Okay, that gets us through the first part of the chapter where you are introduced to the idea behind equilibrium chemistry. Well, let's see, we have one more equilibrium problem. I almost skipped this next one. This says I have 0.6 moles each of nitrogen and oxygen in a 3-liter vessel, and the system was allowed to reach equilibrium. What is the equilibrium concentration of N2 gas? Okay, so in this particular case, I need another scratch sheet. I'm sorry, I did not provide enough space on this question to work this. So let's take a look at this question. So when all else fails, set up the ICE table. So I want to set up the ICE table, and I'm going to have nitrogen gas reacts with oxygen gas in an equilibrium to form 2 nitrogen monoxide gas. The ICE table has initial, change, equilibrium. Now, we're given the KC equation. C stands for what? C stands for concentration. So we have to express each of these terms, each of these values in terms of its concentration. So 0.6 moles were placed in a 3-liter container. The concentration of nitrogen, initially, I put subscript 0, that means at time t equals 0, the initial concentration of nitrogen equals the initial concentration of oxygen, because it says 0.6 moles each of nitrogen and oxygen were placed in a 3-liter container. It's the number of moles divided by the volume. Concentration is number of moles over volume. The number of moles is 0.6. The volume is 3 liters. And so when you get that, you divide that out, then the concentration is 0.2 moles per liter. The concentration is 0.2 moles per liter. So that's what goes on the initial line of our ICE table. We start with 0.2 moles per liter of nitrogen, 0.2 moles per liter of oxygen. Now remember, you have to use concentration and molarity here rather than number of moles, or you will get the wrong answer. Okay? And what's my initial number of moles of nitrogen monoxide? Well, if we put nitrogen and oxygen in the container, we use exclusive language. That means we didn't put anything else in, and initially this is 0. Well, you can tell that Q will have to be 0. Q is products over reactants. I'll have 0 in the numerator. 0 squared divided by 0.2 divided by 0.2 will be 0. It has to go in a forward direction, which means on the change line, we will put minus x plus 2x. Okay, so first of all, notice it's going forward. So x, for every x moles per liter of nitrogen that reacts, x moles per liter of oxygen will also react, but we will get 2x moles per liter of nitrogen monoxide. And so this coefficient, we have to bring that down. Now, draw the line here. This line means equals. 0.2 minus x equals, we'll write 0.2 minus x. 0.2 minus x equals, we'll write 0.2 minus x. 0 plus 2x is 2x. Okay, so that's what we see from the equilibrium line. When all else fails, you do two things. First, you set up the ICE table, which we just did. If you don't know anything else to do, set up the ICE table, and that's what we did. And then plug the equilibrium values into the KEQ equation. So Kc looks like this. Kc is the concentration of nitrogen monoxide squared divided by the concentration of nitrogen and divided by the concentration of oxygen. Kc is given. It's 0.0121. That's the value of Kc. So this is only true at equilibrium. When you divide these out, it only equals 0.0121 if the system is at equilibrium. So take these values from the EQ line and let's plug those in. And when we plug those in, we'll have for the concentration of nitrogen monoxide. What is the concentration of nitrogen monoxide at equilibrium? It's 2x. So we'll have 2x, and that whole quantity squared. Be sure to square the whole quantity. The 2 has to be squared as well. Divided by, and at equilibrium, the concentration of nitrogen is 0.2 minus x, and the concentration of oxygen is 0.2 minus x. So this is 0.2 minus x squared, and that's equal to 0.0121. Now, you do not want to do the quadratic formula on this question. That would take too long. Instead, notice that in this reaction, I've got to solve for x, but this is a perfect square. The numerator is squared, the denominator is squared. So let's take the square root of both sides. That's the easiest way to approach this. When we take the square root of both sides, we will have that 2x divided by 0.2 minus x is equal to the square root of 0.0121. Okay, so we take the square root of that, and here's what we get. We get 0.11. 2x divided by 0.2 minus x is equal to 0.11. So now it's just a matter of solving for x. We need to cross multiply. I will multiply both sides by 0.2 minus x to get that out of the denominator. 2x equals 0.11 times 0.2 minus x. I will multiply across in order to remove the parentheses. 0.11 times 0.2 is 0.022 minus 0.11x. Now let's get all the x terms over on the left side. I'll add 0.11x to both sides, and that would be 2.11x equals 0.022. So we divide both sides by 2.11, and x calculates out to be 0.0104. 0.0104. That's the value of x at equilibrium. But always answer the question that was asked in these equilibrium problems. So up here I want to write, and I'll write again. I know that x is 0.0104. That's what we just found. But always answer the question that was asked. So let's look back at the question. What question was asked here? The question number 13, this particular question says, 0.6 moles of nitrogen and oxygen each were placed in this container. What is the equilibrium concentration of nitrogen, which is right here? And so, therefore, the equilibrium concentration of nitrogen, we go back to the ICE table. The concentration of nitrogen at equilibrium is equal to 0.200 minus X. The concentration of nitrogen at equilibrium is equal to 0.200 minus, and X is 0.0104. And the concentration of nitrogen at equilibrium calculates out to be, whenever we answer this question, we get 0.190 moles per liter. 0.190 moles per liter. So that's what the question asked for. So we use the ICE table, and the concentration of nitrogen at equilibrium is equal to 0.190 moles per liter. Okay, I'll stop there, and the next problem session will cover acid-base chemistry.